Good afternoon, everybody. Today we have Juan Antonio Aguilar Saavedra with us, who has been visiting the IFT already for 1 year. And if nothing strange happens, then he will join us at the IFT within a year or so with one of the positions that were given recently. And he is very well known as an expert, among other things, for top physics. And this is what he will talk about today. I don't know what will he say exactly, but it's called top pourri. And I'm curious about the anomalies and the connection to machine learning that he will talk about. Please go ahead.
Okay, thanks. So let me start with the present, which means the anomalies. Maybe some of you may question, but what the hell are the anomalies? Well, there are a few anomalies in top per production. Most likely, unfortunately, these are unaccounted standard model effects. And these anomalies arise because there have been measurements of differential distributions in top anti-top production and decay to leptons, neutrinos, and of course big quarks. This mode is called the dilepton one because it has, as you see, 2 leptons, electrons or muons. And in this final state, the measurements made by Atlas and CMS are really very precise. And so discrepancies may arise. If you question if I am excited, well, I'm not really excited. Then you can say, okay, but then why you show us these anomalies if you think it's a standard model? Well, because I think it's interesting and one learns things. So the first anomaly and most known is an anomaly in the angle phi, let's call it phi, between the leptons. I will define it later. As you see from the abstract in the Atlas paper, they claim that spin correlation is somewhat higher than predicted by the generators. There are more anomalies in measurements by Atlas, though they don't comment anything in the abstract. The results are compared and they don't say how the comparison goes. A third anomaly is in CMS. They are more bold than the Atlas people, and they say significant disagreement is observed between data and all predictions for several observables. This is a third. And the fourth anomaly is some anomaly that some of you like, an excess in a search for a pseudo-scalar decaying into TT bar. In the abstract, they say a moderate deviation, 1.5 global significance. If they quote the global significance, it's because the local significance is high. And when you go and look, it's a 3.5 sigma, which is something to look at. Let me explain a bit in detail what happens. As I have mentioned, the dilepton final state is quite clean, especially if the 2 leptons have different flavor. In this case, you don't have a background, basically, from Z plus Z. And it is possible to measure several kinematical distributions in the laboratory frame involving the 2 leptons and compare them to the state-of-the-art theory predictions. To do that, you don't need to reconstruct the moment of the top and the anti-top. You don't need the neutrino momentum. Just you need to do some extrapolation to full phase space to compare with generators. And it turns out that the results do not agree sometimes with the next to leading order predictions. In some cases, neither with the next to leading order. There is no working new physics explanation. I did some exploration with Michelangelo, and instead we ruled out some beyond the standard model explanations. There are a couple of talks I gave at CERN with some trials. And I will begin with this anomaly in the angle phi. The angle phi is, as you see, the difference between the azimuthal angle in laboratory frame of the two leptons. Azimuthal means taking the axis, the beam axis. This is quite a clean quantity to measure. You don't need anything, just as I have mentioned, some extrapolation. The anomaly appeared in Atlas data, and since then, both Atlas and CMS obtain similar results that you can see in the plot. In the plot, you have not only the data, but next to leading order, which is here, and next to leading order, which is the flat line. The tension is softened and at next to leading order, and the combination is on the way, and you see that the slope seems different, even from next to leading. So there seems to be an anomaly. This observable doesn't have a clear physics interpretation because it's sensitive to the spin correlation between the two tops. It's convoluted with a boost to the laboratory frame, and it's also sensitive to additional unknown boost maybe of the TT-bar pair in the transverse direction. So instead of studying this observable based on physical quantities, I did an effective framework to study it. So what I did is simply to use a Fourier analysis of the distribution. You see that you can keep 3 terms, and then you can describe well the distribution, as you can see in this plot, and then you can compare the coefficients in the standard model at leading order or next to leading order and in Atlas data. Basically, the first one is a normalization, the first coefficient, 1 over pi. The first one non-trivial roughly gives the slope of the distribution, and the other two do some modifications. There is another interesting distribution that you may look at, and it's not the difference between azimuthal angle, but the difference between the rapidities of the leptons, which is this delta eta, which also can be expanded in a Fourier series. You get a good description to 3 orders. And this can be done to study in a simple and compact way the effect of new physics in these distributions or whatever you like. So what we present in the next slide is done at a leading order, which is justified because the difference to data is quite large, larger than the difference between leading order and next to leading order. And to do the calculations, I parameterize the Fourier coefficient, which is simple, as a function of the new physics coupling. And then I first focus on the first coefficient, try to fit it, and then see if the remaining coefficients, or say the whole distribution, is well reproduced or not. As a benchmark, I used a pseudo-scalar. It was well before the pseudo-scalar excess, but I noticed that pseudo-scalar was a good option. And I used masses below the threshold for 2 reasons. First, because the anomaly appears to be across all the TT-bar invariant, mass invariant range. And also because it's safer for other distributions. So you have a contribution like the one depicted here with an effective vertex. I don't worry why this vertex appears. And a Yukawa coupling to the top. This is the Lagrangian you have for the pseudo-scalar, and the amplitude of this contribution is proportional to the product of these couplings. So in terms of the product of these couplings and doing this Fourier decomposition, you see that this is the first coefficient of phi. This is the Atlas result, and you see the functional dependence on these two, and you see that you have 2 points where you can reproduce at least one coefficient. But unfortunately, you see that for the other distribution that you have in blue, you get away from the standard model. I mean, not from the standard model, from the Atlas measurement. For a mass either of 300 GeV that I'll try, or 100 GeV. And this seems unavoidable. Comparing the two masses, you find that one mass, 300 GeV, when you fit the first coefficient, then the distribution goes okay. And for the other mass, when you fit the first coefficient, the distribution goes very ugly. So this is not an expression, but it's not noticeable that fitting, just introducing the pseudo-scalar, you can fit everything. It's non-trivial. Now let me choose of these two solutions, this one, the one with a negative value. Then you realize that if you introduce the pseudo-scalar to fit the phi distribution, you get 40% extra cross-section, which is excluded. So the explanation does not work. Moreover, this is the delta eta distribution, in which you see that here, larger, that you have a 7% relative shift near to 0. This is completely incompatible with experimental data, so it's finished. There is some caveat, maybe there could be some effect that we don't know working to compensate, but I don't figure out anything. So in principle, this is excluded. But even being excluded, let me have a look at more anomalies. It's curious that when you introduce the pseudo-scalar fitting the anomaly in the phi angle, you get these deviations in the invariant mass of the two leptons, which are somehow in agreement with the measurement. This is compared to Monte Carlo and next to leading order. These two quantities are related, but okay. This even if this is excluded, it's curious to see. There are other distributions that show anomalies. As I mentioned, this is the sum of the PTs of the two leptons. And here, it's hard to see by naked eye, but there are some deviations which are reproduced when you introduce the pseudo-scalar. That does not work, but reproduces this. And in the PT of the lepton, there is also an anomaly in data compared to next to leading order. And when you introduce the pseudo-scalar, again, it seems to work. So it's clear that from the delta, the excess in the cross-section and the delta eta, that a pseudo-scalar cannot explain the deviations, but it's curious to see that this would explain other things. And this is quite non-trivial. I don't have time to explain that in detail, but if instead of choosing this value to fit the first Fourier coefficient, I chose the other one, this one that I have here, this one, then I get much worse agreement with distributions like this and this and this. Okay, so this is non-trivial. And by the way, I tried many other new physics explanations like a scalar, not pseudo-scalar, color scalar, T-channel, flavor changing, whatever, and they don't work to explain everything. A few days ago, a proposal came, Toponium. Maybe you didn't notice the paper by a colleague of mine, Benjamin Fuchs, and other two people. They say that Toponium, which is a bound state of a top and anti-top, which has not yet been seen, could explain this anomaly in phi. Well, Toponium is basically a pseudo-scalar exchange in glue-glue to TT-bar. So it works like the things that I have shown. So the authors of this Toponium paper used a mass of, they got a mass of 344 GeV for the Toponium and a width of 7 GeV. This is what they get from looking at the profile of the cross-section. Then they extract this value for the mass and the width of this state. So let's say, as I say, well, let's try these values. Maybe I wasn't lucky trying 300 GeV, and maybe it's 344 and larger. Okay, the result is that, well, of course, you can reproduce the distribution in phi. you improve a little in the excess of the cross-section. Instead of a 40% extra, you get a 20% extra, which is a lot, but not so. Still, there is a significant deviation in the delta eta, so rule out. The anomalies in these other distributions are explained while you reproduce them somehow. I have not mentioned that, well, if you look at the tails here, it's not exactly the same at the left, at the right, but I'm using leading order. It's expected that if you use next to leading order, this the matching would be better. Still, that is a calculation for the cross-section of toponium production. And it's 2%, not 20%, as you will need to explain this phi distribution. So when you go to the numbers, they claim here that this toponium could amount for that, but when you put the numbers in, you see that it's the excess in the cross-section is 10 times larger than what the toponium gives. So it's not toponium, unfortunately. Let's try next to leading order then. People, of course, when this anomaly came out, people doing next to leading order started looking at this in detail. This is an interesting and unexplained thing. I have shown before this plot on the left, where at the parton level, you have the comparison between, at the parton level means full phase space. As I have mentioned, you need only a little extrapolation to get that from what the experiments measure. You see a different slope from data to next to leading order, but then if you go to the measurements in the fiducial region, the fiducial region is the kinematical region where the measurements are actually performed. In that case, the discrepancy is smaller. On the top panel, you have Atlas. They have to apply more or less the cuts that Atlas uses in the fiducial region. And then you see that, for example, here, that it's closer than it is in this plot at the left. This was done in this first paper. And then in the second paper, they did the same and more things for the CMS fiducial region, which is different from the Atlas one. And you see, there is perfect agreement. It's curious, but in principle, the anomaly seems to be somehow more solved, not completely, but I mean, you don't understand why this happens, but in this region, at least you have better agreement. Now, these people, I liked a lot this paper, which I studied when preparing this talk. They also compare other distributions which have anomalies. For example, the PT of the lepton that I shown before, and the sum of the PTs of the two leptons that I already shown. And I saw that with the pseudo-scalar you improve, but also at next to leading order, you improve. And you see agreement here. Well, there is some being here, okay. And in this one, you see agreement. So these discrepancies seem to be solved. There is some exception, however, the invariant mass of the two leptons. This is next to leading order and fiducial region. So now extrapolation. There are some people in this paper claiming that it might be some Coulomb resummation effect, remaining that is some correction. I don't know, let's see. But for the moment, anomalies seem to be quite solved. And what about the pseudo-scalar excess? Well, you have to look in detail to figure out what may be happening. Well, in this CMS set, they combine two channels. The dilepton one, which is this very clean channel that I have been talking about, and which has many apparent discrepancies, and the semileptonic decay channel. In both channels, they use the TT bar invariant mass, in which you expect to see a bump if you have a new resonance. In the dilepton channel, they also use some angle, call it theta, between the two leptons in the rest frame of the parent quark. A bit complicated angle, but no problem. But for this angle, there is agreement from other measurements. So apparently the discrepancy, the excess they find at 3.5 sigma doesn't come from this distribution. And also in the single lepton channel, they use the angle between the top decaying leptonically and the TT bar momentum. This would correspond to an isotropic distribution in case you produce a scala. Well, I don't have plots for this. A curious thing is that the excess appears is highest at 400 dB, and the surge precisely starts at 400 dB. It's quite curious, very suspicious. So it's not like a bump in a sort of smoothly falling spectrum. You see a bump and you say, okay, I have a resonance. No, it's in the lower end of the search interval. So suspicious. And then one comes again to next to leading order. This is extremely funny. The TT bar invariant mass distribution, a threshold, is sensitive to the neutrinos coming from the semileptonic B quark decays. What happens when you do the calculation in the standard model at whatever order? You have the B quarks and the momentum, blah, blah, blah. When experiments measure it, they measure the momentum of the B, and in some cases, you have a semileptonic decay and some neutrino escaping. So this is not precisely the momentum that the B quarks have. So to compare apples with apples, CMS did some unfolding of the B quark momenta to also include the calculated somehow neutrino contribution. And these are the black dots that you see here. And the calculation without this correction are the gray dots. And you see how large is the effect near threshold of including or not including this small contribution to the momentum of the neutrinos. So that's it. This is the bump in the TT bar invariant mass spectrum. The neutrinos from the semileptonic BDK, apparently. Because you see that if you include everything correctly, next to leading order is quite close to data. So the future. Let's begin with a spoiler. How much time do I have? 26, okay. At the LHC, we are often dominated by systematics because we have quite a lot of data. And just adding more statistics often does not help. But feature colliders like high luminosity LHC and whatever, there are many different things that you can do besides accumulating statistics and repeating what you did. One thing that you can do is to explore the top properties at a higher energies, high Q. I will mention that in this talk. Another thing that you can do is to go and explore rare processes. For example, this one I have briefly mentioned. This is a rare decay. The branching ratio is 10 to minus 15 in the standard model. And usual searches at the LHC target the dominant decay mode of the Higgs. Higgs to BD1. Well, if you have quite a lot of statistics, you can target this other channel, Higgs to photon-photon. You have fewer statistics in principle for a same value, for the same value of the efficiency coupling, but systematics are smaller, blah, 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 and this channel may be interesting and maybe the dominant one. There are also a couple of other things that you can do. You can explore the weak regime, the weak coupling regime of new resonances. I will show a few examples. And you can also measure precisely fully differential distributions. Let's begin with proving the top at the highest energies. Well, there is an easy way to prove the top quark, which is the chromomagnetic dipole moment, because it's involved in the production of the top quark. This chromomagnetic moment, and also chromoelectric, can be implemented as this Lagrangian, which is invariant under SU3, and with a constant chromomagnetic and chromoelectric dipole moments. This Lagrangian is what would correspond to a dimension 6 operator. If you include dimension 8 operators, then you have the same, but with an additional dependence on Q squared in dV and dA. But at the first order, at dimension 6 operators, you get this Lagrange. Then what you are doing actually is, like I have the nice picture here, looking at the top and inside the top with a gluon lamp. The reason to look it with a gluon lamp is the size of the coupling, which is this strong, and the fact that you produce TT-Bar pairs in glue-glue fusion at hadron colliders. So there is a great potential. If you have anomalous chromoelectric or chromomagnetic dipole moments, they enter in the production mechanism here twice. By the way, I'm calling this term anomalous by analogy with QED. When the sigma mu nu term, you call it anomalous magnetic moment because it's not the usual 2 magnetic moments, you call it G-2. And this, of course, this anomalous magnetic chromomagnetic moment arises in the standard model. It has a value of 10 to minus 2. This is in the standard model. If you have new particles, new forces, whatever, or if the top quark is composite, then you will have extra contributions to this on other observables, and this value will be enlarged. In case you miss the point I want to make, surely you have heard about G-2 of the mu, and you are eagerly expecting for April 7th to see what the measurement is. Well, this top chromomagnetic dipole moment is, so to say, the colored version of the G-2 for a top quark. And the good news is that we have just entered the era of the top chromomagnetic dipole moment measurement, with a measurement by CMS giving this result. Some time ago, the people and me explored the potential of LHC and feature colliders to probe this chromomagnetic and also the chromoelectric dipole moment. You see this plot summarizing the potential of different colliders. And at that moment, LHC at 14 TeV was expected to probe these couplings at the level of 2 times 10 to minus 2. This is what you roughly see from this region, this dark brown region in this plot. The light green region is a combination of LHC data at 8 TeV and Tevatron. They have strange shapes, but don't worry. Well, our projection 7 years ago has been exceeded by the measurement by CMS. We expected 2 times 10 to minus 2 precision, and they already have 10 to minus 2 precision with the first bunch of run 2 data, which is quite good. And by the way, this measurement has a large error, but agrees with the standard model prediction that you have here by these people. For the FCC, you can see the comparison here in this plot. It is expected to prove these anomalous terms to the level of 3 times 10 to minus 3. I will give details later, a few details, but for the time being, these calculations are done by using the dependence of the total cross-section, either inclusive or at a high invariant mass on these couplings. You parameterize it, and then you get once you impose that you have an experimental measure, or you assume some experimental measurement with some precision, then you get the constraints or the expected constraints on these quantities. Now, another thing that one can wonder is, okay, how far can we go to probe if the top is elementary or it is made of some prions or whatever? There is an easy way to do that. You implement this Lagrangian, in which this quantity here corresponds to the so-called top-color radius, and then you look which constraints do you get on this number. Put it in usual quantities. It's 10 to minus 20 meters, and you can compare this quantity, which is the top radius that will be probed at the FCC. FCC, if I have not mentioned, it's 100 TeV. You can compare this length with lengths of other popular objects. At the energy frontier, it's very useful to go to as high energies as possible to prove the effect of the dimension 6 operators. Not only, as I have shown, for chromomagnetic moment, but for all kinds of dimension 6 operator, because the effect of the extra contribution beyond the standard model grows with the energy. In the sigma mu terms, like the top chromomagnetic moment, you have a derivative here, giving a momentum factor extra compared to standard model amplitudes. In the 4 fermion terms, you don't have an propagator suppressing. So the contribution, the anomalous contribution beyond the standard model contribution grows with energy compared to standard model. On the other hand, of course, cross sections decrease with Q, and the PDF decrease. So the effect is enhanced, but you also have a larger systematics and smaller statistics. So there is some balance. Then, for example, in this example, you don't go to, if you have a 100 TeV machine, well, the best sensitivity is achieved at invariant masses of 10 TeV or so. You have a balance between the effect of the anomalous contribution and the statistics and systematics, but overall, you have an improvement. There are other situations where at a future circular collider, going to high energies can help. In flavor changing interactions, for example, in this flavor changing production of a top quarks with a cell or a photon, and looking at precisely at the dominant coupling of the standard model, which is TeV W. This is a summary table for FCNC from that paper, and you actually see that, well, basically the best prospects are for FCC at a high Q. And now, besides effective operators, dimension 6 operators, I will go to the other thing I mentioned, which is to prove the regions of a small coupling of new resonances. When you see a summary plot by an experimental search, the experiment gives some upper limits on cross-sections time branching ratio as a function of mass. This is the line with points. You have the expected limit plus minus 2 sigma, and then you have the observed limit. And experimentalists like to draw lines, this red line, to compare with something. They, in this case, draw a line. This is a search for a W prime decaying into top and bottom. The W prime with a right-handed coupling, and they compare with a prediction for a right-handed W prime boson, which coupling? Well, equal to the SU2 coupling G, and then they draw the line. And then even they may claim in the abstract, we exclude W prime up to 3.4 GeV. This is misleading because they are excluding them for this value of the coupling. Of course, we all know that. But it may be tempting to forget this region here. And sometimes this happens. The searches with more luminosity don't keep the lower mass region. They just say, okay, let's forget and let's go higher in mass. And this region is interesting. Fortunately here, they have shown it and they perform the search, but this is not the case all the time. Well, feature colliders, in particular for a top quark, are very useful to probe this because of the high statistics. Not going to high Q, which was what I was discussing regarding the topomagnetic dipole moment, but already in the low Q region, because you have a lot of statistics. So if the excluded values of the coupling from this CMS sets are these ones, well, you expect to have 5 sigma sensitivity of the values in this table at high Lumiere LHC, high energy. This machine won't be built, but we have numbers for these two, and of course at FCC. So it's an interesting exercise to know that even if we have very weakly coupled new resonances, we will be able to see them. And of course, for what a 100 TeV machine works best is to go to high masses. The potential of a 100 TeV when you go to explore higher masses and larger coupling is impressive. For a coupling, the coupling preferred by benchmarks, which is to set the G prime equals to the G of the standard model, then you exclude up to 30 GeV of W prime decaying into top and bottom, and light quarks. Now let me explain, what time is it? 41, right? Okay. Let me explain what is the problem with this analysis. The problem is clear. When you get a very energetic top, the decay products merge into a single jet. So what you have, in any case, even if you have the top decaying to leptons and a B, you have a jet here and a jet here. Jets are produced quite a lot by QCD interactions, so the measurements are way more difficult. In this analysis I have mentioned, you have to use the features you have at hand to try to reduce the jet background. For example, the jet mass, you have a plot of a jet mass for a signal and a background here. It's not very different. Substructure, you have the substructure here for the signal, the solid line, and the background, the dashed line. Not very different. You can gain something. Also, if you go to the hadronic, the leptonic decay of the W, you have a charged lepton, and then you can plot as a function of the charge, the fraction of momentum of the charged lepton inside the top jet. There is some difference between signals and backgrounds, and then you improve. The bottom line of showing this plot is that their measurements with ultra boosted tops, potentially they have great sensitivity, but the analysis are quite more difficult than at the lower energy. Then this motivates the third part of the top purri. What else can you do? Of course, machine learning. There have been methods developed to identify jets by looking at the subtraction, which is called prongness. Basically, even if you have a large radius jet, you can look inside. This is the guy looking inside, and then you identify that maybe you have only one core, or you have some structure with two nuclei here, or maybe you have three. I mean, the pions and kaons and blah, blah are concentrating. This one prong corresponds to a quark or gluon. This two prong corresponds to WZ or Higgs going into two quarks, and this three prong corresponds, for example, to a top quark decaying hadronically. The quarks and gluons are always the background, and the physics signals often involve boosted tops and WZ. So the discrimination using these tools is usually done of some signal, top, W, versus quarks and gluons. For example, you have here a distribution called tau2-1, which is used by CMS to discriminate Z and W bosons from jets. This is a distribution for several values of the parameters for the W or the Z, and this is the distribution for a quark or gluon jet. And then you see that they are different. You may cut here or here, discard what you don't like, and then you reduce the background. But this can be improved using machine learning. Broadly, machine learning tools use two methods to discriminate the boosted jets that you want to explore from some signal from the background. Either using high-level inputs. High-level means some observable that parameterizes the distribution of the particles between the jets. Or low-level, which is just like taking a picture of the calorimeter, treating that as an image. Apparently, the discrimination power in both cases is the same. And if you want to measure the performance of some machine learning tool to discriminate tops or whatever versus the background, what you do is to go to a plot called receiver operating characteristic plot. It's usually ROC. This is, for example, the ROC for discrimination of top quarks of several neural networks, deep and shallow neural networks, and discriminating the tops from the quarks and gluons. And then to read this plot, you go to the signal efficiency is usually on the x-axis, and you can see, okay, for a signal efficiency of 0.5, blah, 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 I go here to the line, and I get 1 over the background efficiency. 1 over the background efficiency is the background rejection. So you reject QCD jets by a factor of 500 while having an efficiency of 0.5. For reference, this is for top tagging. For B tagging, CMS has, for an efficiency of 0.5, has a rejection of 1000 for light quarks and 50 for C quarks. Now, the same can also be done for top quarks with leptons or Higgs boson with leptons. I mean, jets which have charged leptons, energetic charged leptons inside. How? You use high-level inputs for the top or the jet substructure, like for unusual tagging. In addition, you can use as input to the machine learning tool the energy fraction of the lepton that you can see, you can identify it, and the delta R to the jet axis. And also, you can use the jet mass and the transverse momentum. This method, I called it FEST, and it's developed building upon a previous method called MAST. And with that, a tagger can be built to discriminate at the same time, not only between one signal and the background, but between two signals and the background, between Higgs decaying semi-leptonically, which this gives when boosted, this gives a jet. At top, decaying semi-leptonically, in which this is a jet, and quark and gluon jets, which also have leptons from the secondary decays of the Bs and the Cs, etc. And this can be done over a very wide range of PT, and that is important. Let me explain MAST briefly. It's easy to understand that these variables that parameterize the jet subtraction depend on the PT of the jet. Imagine that you have a top or whatever decaying like this, giving a jet. When you boost it more, the decay will look like this. Then the variables, of course, depend on the PT. There is a dependence not only on if the jet corresponds to a top or a background, but also on the PT of the jet and also of the mass. Usually, the targets, the hadronic top targets, are trained on some narrow intervals for the mass and PT. These targets, for instance. These are neural networks trained on some narrow interval of mass and PT. If you apply these targets outside this interval, the performance is, of course, degraded. You can do something which is to make 100 neural networks, and then each one for one interval, and then you use this 100 neural networks in your data. This is cumbersome, and this would give problems in the boundaries of the intervals. The solution is what we call mass and specific supervised tagging, in which both the mass and the PT of the jet are included in the training of the neural network. This was a paper by me, Felipe, and our PhD student. Now, building upon that, you can apply also this method for tagging jets with leptons, in which you use some variables parameterizing the subtraction, also the mass and PT, and as I have mentioned, the energy fraction and delta. I will skip these technical details and just show the first. You have here the rock for Higgs discrimination versus jet. It's a three-class discrimination. I mean, the target, it's a three-class: Higgs, top, and jet. But you may be interested on discriminating Higgs versus jet. This is what I show here. And you see that for an efficiency of 0.5, you get a rejection above 5,000 for jets that already have a lepton, which are scarce. Keep it in mind. You get a huge rejection of QCD jets, and the neural network performs wonderfully. I will skip the details, but it wasn't easy, as I say. You may also be interested in discriminating tops versus jets. And then you plot the rod, and you see, again, an excellent discrimination. For a reference efficiency of 0.5, you have a background rejection of 5,000 and more. By the way, let me emphasize again that this is a single target working on all this PT range. It's not an array of targets. It's a single neural network that discriminates among top, Higgs, and jet, and for any PT, which I think it's wonderful. And finally, you can be interested in discriminating tops from Higgs, or more commonly, Higgs from top. Usually, the Higgs production has a lower cross-section than top production, and you may have processes where you look for a Higgs signal, and you have a top background. Then, again, this neural network can do a wonderful discrimination, not as high as for light jets, but the figures are very high. For a Higgs efficiency of 0.5, you have a rejection of tops by a factor larger than 100. On top of that, I have time. I have already mentioned that energetic charged leptons are scarce in QCD jets. they come from secondary decays of B's, C's, and so. So when you take that into account, what you have at the end is that your rejection for QCD jets is a factor of 10 to 4 or 10 to 5 for an overall efficiency for tops and Higgses of 0.5. So I believe this type of tool will be extremely useful to improve the sensitivity for the top. To begin with the analysis I have shown for boosted top quarks at the energy frontier, or whatever you imagine with boosted tops. For Higgs, for example, if you look for resonances decaying into 2 Higgs, W Higgs, Z Higgs, or whatever you imagine with boosted Higgs bosons. And the last slide, it's an example, not for the top, but for the Higgs. Example of potential search. Well, this is your QCD background, huge. Already, when you require a lepton in the jet, even if requiring that you have, it's a search for a resonance, a Z prime decaying into a Z and a Higgs boson in the jet final state, and the background is as large as this, even after requiring that one of the jets has one lepton. Well, after applying some cuts and applying the target, you inject a signal and you can see it. Precisely the size of the signal injected is the upper limit from an analogous search, where instead of using this target to identify the Higgs, you use the decay to be debugged. So to finish, I will not make a summary. Instead, I will share my thoughts with you. First, about the anomalies. Well, it's apparently not new physics, but it makes me happy. This, what has happened with these anomalies and the study, and how the measurements can be refined and the predictions have been refined, make me quite certain that we are capable to see indirect signals of new physics at Hadron Collider, not only at LHC. And quoting my chairman, it's not necessarily that all anomalies are confirmed, just one of them. So I'm not unhappy overall. I want to point out again that future colliders often offer interesting possibilities beyond merely repeating the same analysis done at LHC with more luminosity. You can change and imagine things that are completely new, like some examples I have shown and more. Amazingly, for the top quark, there are very few sensitivity prospects for FCC, which is the most popular machine for the far future. There are interesting things also to do at LHC, of course. And you can realize that together with the machine learning, this having brand new possibilities for analysis plus machine learning is quite interesting, and there are many possible things and interesting to do. And that was all. Thank you.
Thanks a lot, Juan Antonio, for this broad overview of possibilities and anomalies around the top. Are there questions or comments?
I have one. Can you listen me?
Maria Jose, go
Yeah,
ahead. Yes.
I can hear you.
Yeah, even if I look like Zoom 2 IFT, I am Maria Jose.
Yeah, I know your voice.
Yes, hi, Juan Antonio. I am curious about one thing. Coming back to your anomalies studies in top anti-top production.
Let me go.
Yeah?
Yeah?
No, I don't need to go to the plots.
Okay,
it's just
then I
curiosity.
stay here.
Most of the anomalies that you were mentioning use the semi-electronic decays of the top and anti-top, where you make profit of the information which is very clean from the leptons that come from the decays of the top. So you get a positive lepton from the top decay and a negative lepton from the anti-top decay. Great. Yep. And then many of the asymmetries you were commenting appear in particular in distributions in the invariant mass of the two leptons together. Okay.
Yeah.
Now, my question is, have you studied, or other people, the correlated potential anomaly that could be building the invariant mass of the two jets B tagged coming from the decays of the top and anti-top? Meaning,
no.
use the B tagging with the techniques that you are.
Yeah, sure, sure. I think there are plots for that, for sure.
So
and
the
I don't
question
remember
is,
any anomaly.
Antonio, wait. The question is, do you find anomalies in such a variable, which is obviously correlated with the previous ones?
No, it's not obviously correlated.
It is, because they come both, the B jet come from the top decay and the lepton comes from the top decay. And the same for the other hemisphere, where you find the anti-top decay. So yes, they are correlated.
No, not necessarily.
Where you have two
because,
jets tagged, one in one hemisphere and the other one in the other hemisphere, and you are assuming as the main candidate, which is a top decay into that, there is a correlation between the distribution of the events in the invariant mass of the two leptons, two charged leptons, and the. You understand my point?
But
and the corresponding
let me
mass
answer.
of the two jets.
Yeah, I know the kinematics, but let me answer. Well, okay. Correlated, yes, I admit that, but the correlation may be very weak. In particular, because the charged leptons has spin analyzing power equal to 1, so has a great correlation with the top spin, while the bottom quark has a spin analyzing power of 0.4. So the correlation is weak. It's much weaker.
Not really, because the lepton comes from the decay of the top into 3 particles, whereas the bottom roughly carries half of the energy of the top, because it decays into the top and a W, into the bottom jet, B jet, and a W, that then decays to the lepton and neutrinos. So why not use such information, which is great, and with the techniques that you have at hand, which is with machine learning, you may reconstruct the B jet very well.
I don't think, first of all, I will have to look up in the plot, but I did not notice an anomaly that in that distribution. Of course, anomalies could appear there, but the angle. Don't forget that when you plot the angle between the B's, you are plotting the angle between two jets, which is a wide thing, and the resolution for the angle and the rapidity. Everything is way worse than for the leptons.
Yes, but you have more statistics.
No, you have the same statistics.
Yes,
each event has each event has a charged lepton, 2 charged leptons, and 2 big quarks.
Well, we can speak about it, but my convention. I mean, I think that you should get also, of course, weaker, but also an anomaly in such a variable.
Well, the fact I can look in the papers and put to the figure. I don't think there is any anomaly.
Okay, all right. No more questions. Thank you.
Thanks a lot.
Thanks.
More questions or comments? Let me ask a question. When you were talking about the decay of a heavy object into TT bar, and you were mentioning this analysis that saw the axis at 400 GeV by CMS, you were always talking about a bump. If I remember correctly, the problem of this analysis is that with the background interference, you get a bump dip structure, or depending on other signs, a dip bump structure, which makes it much more complicated to search for it. It's not that you just see a bump over a smoothly falling background, but it's a much more complicated signal.
But usually,
I mean, if you look at the invariant TT mass distribution, you don't just see a bump at where this, for example, new Higgs boson is sitting.
Well, usually those effects happen. Well, they happen because of the interference, yes. But they are not measurable normally because of the, because you have some some wiggle in the distribution, and when you put the detector resolution, then all the wiggle away. Then I'm curious why the excess in the pseudo-scalar and not at the scalar. Maybe, I don't know.
I think this is because of there are different peak dip structures, and also the production cross sections are different. Yeah, so
maybe the dependence on the angles. Yeah, maybe that.
Yeah. But okay, I'll look it up again.
Because
I was sure that they look for this peak dip structure. Therefore, I was
not so sure.
Okay, I'll look it up and we'll discuss it afterwards offline. Yeah. Good. I do not see any raised hand. Nobody wants to take up this opportunity. Then thanks again for this, as I said, very broad, and for me at least, it looked quite complete overview of the anomalies that there are and the possibilities that they're out there. And thanks a lot again.
Okay.
Yeah.
Thanks to you. Bye.